Economic order quantities is the optimal size for an order in a simple inventory system. This analysis for this was done early in the last century, and it remains the best way of controlling many stocks with independent demand. It is flexible and easy to use and gives good guidelines for a wide range of circumstances. Imagine a single item that is held in stock to meet constant demand of D per unit of time. Assume that we know the unit cost U, reorder costs R, and holding costs H. But the shortage cost is so high that no shortages are allowed and all demands must be met. The item is bought in batches from a supplier who delivers after a constant lead time. We want to calculate the best order quantity Q. There is no point in carrying spare stock, so we time orders to arrive just as existing stock runs out. Then we get a series of stock cycles where the stock level follows the sawtooth pattern shown in this figure. At some point, an order of size Q arrives. This is used at a constant rate D until no stock is left. We can find the total costs in each period of time by adding the four components of cost, the unit, reorder, holding, and shortage. No shortages are allowed, so we can ignore this component. The number of units bought each period is D, so multiplying this by U gives the unit cost component UD. The average stock level is Q divided by 2, so multiplying this by H gives the holding cost component HQ divided by 2. The average number of orders in each period is D divided by Q, and multiplying this by R gives the reorder cost component RD divided by Q. Adding these cost components together gives the cost per period. This is the unit component plus reorder cost component plus holding cost component. The unit cost component does not vary with the order size, but if you plot the other two components separately against Q, we'll get the results shown in this figure. Here you can see that the reorder cost component falls as the order size increases, confirming that larger orders give fewer orders and lower reorder cost components. The holding cost component rises linearly with the order size, confirming that larger orders give high stock levels and higher holding cost components. Large and frequent orders give high holding cost components and lower reorder cost components. Small frequent orders give low holding costs and high reorder cost components. Adding the two cost components give a total cost curve that is an asymmetric U-shaped with a distinct minimum. This minimum variable cost identifies the optimal order size. The minimum cost occurs when the holding cost component equals the reorder cost component, or RD divided by Q equals HQ divided by 2. We can use this last observation to calculate the economic order quantity, as rearranging the equation gives this result. EOQ is square root of 2 multiplied by R by D divided by H, where D is the demand per unit of time, R is the reorder costs, and H is the holding cost per unit of time. Now, let's continue with one example. Jane buys stationery for ABC Company. The demand for the printed forms is constant at 20 boxes a box, or 20 boxes a month. Each box of forms costs $50. The cost of processing an order and arranging delivery is $60, and the holding cost is $18 per box per year. What is EOQ total cost per year and the length of the stock cycle? Listing these values, we know in constant units, we find D, 240 units a year, U is $50 a box, R is $60 per order, and H is $18 per box per year. Substituting these values into the economic order quantity formula gives 40 units. So Jane should always order 40 boxes at a time. Then the cost is the unit cost component plus a reorder cost component plus holding cost component. which gives us $12,700.20 a year. Jane buys 40 boxes at a time, so the average stock level is 40 divided by 2. This is 20 boxes. By buying 40 boxes at the time and using 20 boxes a month means that the stock cycle is 2 months long. This means that Jane places an order every 2 months. In general, the length of the stock cycle is T, which is Q divided by D. In this case, this is 1/6 years or 2 months.